of the notes packet you got yesterday. So we came up with the parent functions for sine and cosine yesterday using our unit circle and a calculator. So here are all of the properties of those sine and cosine functions. Here's the graph. We came up with those yesterday, that you have those on the second page of the notes packet. Okay, remember, get a highlighter here. We said the sine graph, we graphed from 0 to 2 pi or 0 to 360, just this little portion. And then we talked about what would happen if you went past 2 pi. We said the pattern would just continue. And so you can see it here continuing in both directions. It's this same wave just oscillating back and forth between 1 and -1 in both directions. Okay, and then we had graphed cosine. And the portion that we graphed looked like this here. We just graphed from 0 to 2 pi, but we said the same thing. It's the same wave. It has the same domain and range. The only difference is it has a different y-intercept. And you can see that here in the details up here. The y-intercept is different for these, but the domain and range are the same. So it's like the cosine function was just shifted over slightly. From this, it was the sine function shifted over a little. Y'all really don't need to know all of the rest of these details. Don't worry about this notation. That's a special notation that we're not going to be using. But you do need to know the domain and range. You need to know the intercepts, and you've got to be able to distinguish between these two pieces, starting in the middle, going to the maximum, back through the middle to the minimum, and back to the middle. Okay, this is the sine curve. Okay, and cosine goes high, middle, low, middle, high. So a high point to a high point, that's a cosine. Okay, so what we're going to look at underneath here using those is we're going to talk about what's called the critical points. So you should remember back when we were doing the unit circle last semester, we said that we learned and memorized all of the 8 special 30, 45, and 60 degree reference angles all the way around a full rotation. Okay, but when you hit the X and Y axis around the unit circle, do y'all remember what those were called? Like, so 0, 90, 180, 270, 360. Quadrantals, right? The quadrantals, exactly. So our critical points, which you'll see me abbreviate a lot, CP, okay, those are the quadrantals. Okay. When we graphed the parent functions yesterday, we graphed all of those special reference angles and it came out to like 0.5, 0.7, 0.9, right? Do y'all remember that yesterday? We're not going to have to graph all of those every time we graph a sinusoid. We are only going to graph these critical points, and there's 5 of them because it's in degrees, it's 0, 90, 180, 270, and 360. In radians, you can see here in these tables just beneath this, we're going to be using radians more often. It's 0, pi halves, pi, 3 pi halves, 2 pi. Okay, but those are our quadrantals. And so those are the 5 points we plot to graph. We are not going to worry about plotting all of the 30, the 45, the 60, etc. We're just going to graph these 5 points, the 5 quadrantals. Those are going to be the maximums, the minimums, and the points right in the middle. Okay. So for sine, we said sine starts in the middle, and then it goes to the maximum, back to the middle, down to the minimum, back to the middle. Okay. And that's the sine curve. So that high point is where? What's the maximum? 1. And what's the minimum? And if you're on the axis, you're at 0. So these, where I put the points, those are the critical points, the angles. That's 0, 90, 180, 270, 360. So the y value here is just the 1, the 0, or the -1. So y's pattern, it starts at 0, goes up to 1, back through 0, down to -1, back to 0. For cosine, cosine starts high and ends high. So it starts up at 1, down through 0 to -1, back up through 0 to +1. So when we are graphing, we are always going to start with these two columns for a table of values. These are the parent functions. I was about to say bless you, but you're hiccuping. Sorry. No, you're good. We're always going to start with these two columns. These are the parent functions, ordered pairs for the 5 points we're plotting. And then we change things from here. We'll either add columns to the right to change the y value. So if the graph is, the y values get higher or lower, or we'll add columns to the left if our x values need to change, depending on whatever the transformation is. For the sake of our notes and learning this initially, I'm going to create tables. I have the tables drawn for you, and we're going to fill them in, and then we're going to plot the points, because I think that helps a lot of people with graphing, is having a table that you're graphing from. When you start to get the hang of this, you're not going to have to make a table of values every single time. I'm not going to grade your table of values. Some of you are more quickly than others going to get to a point where you can just picture the parent function and make the changes that need to be made and know where those 5 points are going to end up without making a table of values. Some of you, maybe you'll make a table of values all the way through, and even when you're testing, you'll want to make a table of values, and that's fine. Okay, but just know we're starting with these two columns when we make tables of values, and this is what we work from to come up with the transformed function. Does that kind of make sense? I'm always going to label these columns. The column with these 5 angles, I'm always going to label CP because those are the critical points. Okay, and then the column to the right of that, I'm always going to label the trig column, and that's either going to be the sine or cosine values. It's going to be these 1s and 0s. Okay, so far so good? All right, so the first thing we need to talk about is we are showing just that small portion of the sine and cosine graph. We said the domain is all real numbers. It goes on forever, but we're only looking at a portion of it from 0 to 2 pi, because that represents one cycle. Okay, a cycle is just the portion of the graph from one point to a point where it starts repeating itself. Because if it's like thinking back to the unit circle, if we went around one rotation, if we went past that, that's when we started hitting coterminal angles. Okay, so we don't need to do that because we're just being repetitive at that point, because we're hitting all the same points over and over and over. So we really just need to focus in on one single cycle of our graphs. That's all I'm going to ask you to graph, is one cycle. The general form of the sine or cosine functions look like this. The only difference being one says sine here and one says cosine. The rest of it's all the same. So you'll have an A, B, C, and D are 4 places that numbers can appear that will change your graph. So an A is a coefficient outside the function. So if the function itself, the trig function, is being multiplied by something, that's your A value. Okay. Inside the function is B as a coefficient on your X, or sometimes we'll use theta there. Okay, but if you have a coefficient inside the function, it's part of what you're taking sine or cosine of, that's the B value. Okay, and then you can also have numbers that are added or subtracted instead of being multiplied. So if it's added or subtracted on the inside of the function, that's C, and if it's outside the function, that's D. Okay, and over the next few days, we're going to talk about what A, B, C, and D do to your graph. Okay, the first one we're going to focus in on today, though, is amplitude, which comes from the A value. Oh, real quick, I kind of skipped over this. I used this word yesterday when we were graphing the parent functions. I told you that was called a sinusoidal wave. Okay, so any form of sine or cosine, any equation with sine or cosine in them is called a sinusoid. Okay, so that's just a new term. So when you hear me say sinusoid or sinusoidal, that just means it's a sine or cosine function. All right, so amplitude is the first change that we're going to look at, and it comes from the A value in your sinusoid. Okay, so the number multiplied in front of sine or cosine, okay, is going to help us determine what the amplitude is. How you actually find the amplitude is the absolute value of A. Okay, so A itself can be positive or negative, but the amplitude will always be what? Positive, because when you take the absolute value, you always get a positive. So your amplitude is always positive. So if your question asks, what is the amplitude? Do not give a negative answer. If it's multiple choice, do not select a negative answer. The amplitude is always positive. Now, what the amplitude is measuring is the distance from a maximum or a minimum to the middle of the graph. So it's half the distance between the maximum and the minimum. So here's a maximum. Here's a minimum. So the total distance between the maximum and the minimum, that's the height of the graph. The amplitude is half of that. So see this dashed line down the middle? That's the halfway point. So the amplitude is here from maximum to the middle or from minimum to the middle. They're equidistant. Those are it doesn't matter which one you measure from, max or min, because they're the same distance to the center. Okay, so the amplitude is half of the height. Now, that dashed line that we drew down the middle here has a name. It's called the midline. It's the equilibrium of the graph. It's that center. On the parent functions, where is that? What's that midline on the parent functions? 0. It's the x-axis. Okay, because the high is at 1 and the low is at -1, so the middle is at 0. Okay, but once we start transforming our graphs, that midline can shift up or down. Okay, we're not going to get to that today, but we will tomorrow. Okay, but that's the midline. The amplitude is the maximum to the midline or the minimum to the midline. All right, so let's look at actually graphing. For the sake of our notes, I said I'm going to make a table of values. Eventually, you'll get to a point where you may not need to do that. And for the sake of our notes, I'm always going to have us put the parent function on there so that we can compare them together, see them together. When you're doing your practice starting out, that's might be a good idea is to put the parent function there, like real light in pencil, and then like darker, do your actual graph so you can see the comparison. Or if you have 2 colors, do it in 2 colors. But like when we test or take a quiz or something, you're not going to have to graph the parent function with the new function. Okay, that's just something we're doing as we learn it. So the sine parent function, we said if these are our critical points, so these are the angles, those 5 quadrantals, okay, sine goes 0, 1, 0, -1, 0. Okay, so those are the two columns we're starting with. I'm going to label that one as my critical points and that one as my trig. And I'm going to plot those points, and that's my parent function. So at 0, 0, at pi halves 1, at pi 0, at 3 pi halves -1, and at 2 pi 0. And I'm going to remember it's curved. Don't draw straight lines with sharp points. Nice and curved. So there's the parent sine function. Now we're going to figure out how that changes when we have this 3 in front. We want to graph 3 sine of x. So the a value is the 3. So it's being multiplied in front of the trig function. So what that tells me is my amplitude is 3, because the absolute value of 3 is 3, right? What's the amplitude of the parent function? 1, right? So this is going to have to get taller to have an amplitude of 3. Okay, so we're going to use the table of values to help us figure out what that's supposed to look like. So when you're doing your table of values, what you are taking sine or cosine of, whatever's inside your function, that's always what goes here as the title or the header, whatever you want to call it, of that critical point column. Okay, so in this case, it's just x. So that our x column is done. We've got x because there's nothing inside affecting the x or changing the x. Okay, our trig this time is sine, we said. So it's sine of x. Okay, then if you have an a value, and we need to have a column to the right of your trig column to account for that. So then this is 3 sine of x. So what you do from your trig column to the right is you're multiplying by a, whatever that a value is. In this case, it's 3. So I'm going to take these numbers and I'm going to multiply them by 3 to get my new column. So the zeros obviously stay 0. 1 times 3 is 3. -1 times 3 is -3. Once you get the column like header or title here to be the entire equation, the entire function, which here it is, you're done. You're to the right, you're done. That's your y column. And on the left side, once you have x all alone, you're done. That's your x column. So the far left column are your x's and the far right column are your y's. So I'm going to plot those points. So 0, 0. So that didn't move. Pi halves 3. Pi 0. 3 pi halves -3. And 2 pi 0. And then I'm going to sketch that curve. So that's the new function. That's in black. The thin black line is sine of x, and this darker green one is sine of x. How would you describe them? How would you compare them? What happened? What's the change? What type? Vertical. So this is a vertical stretch. Like you'd put your hands on top and bottom and pulled them apart. You stretched it vertically to make it taller. Okay, I'm also going to have y'all get in the habit of labeling your graphs with the key features like amplitude and period. So the amplitude, I'm always just going to label with like a little dotted or dashed line from the maximum to the midline or from the minimum to the midline. And I'm going to use a capital A. So what is the amplitude here of this graph? 3. Is that what we said it should be based on the equation? Yeah, so it's kind of like a check for yourself as you go. It's like, okay, yeah, that checks out. I thought it should be 3. When I graphed it, it was 3. That's good. And then I want y'all to label the period. The period is like the width of the graph. Okay, how wide is it? So from starting point to ending point of this sine cycle, I went from 0 to 2 pi. So that's a distance of 2 pi, right? So my period is 2 pi. The parent function's period was 2 pi, right? So there's no change to the period. It's the same as the parent function. So it did not get wider or narrower. It got taller. So far, so good? All right. What if we change that a value to a 1/2? So now instead of 3, a is 1/2. What does that mean your amplitude will be? 1/2. So instead of getting taller, what's this graph going to do? Yeah, it's going to compress. It's going to be shorter. It's like we're going to put our hands on top and bottom of the parent function and squeeze it in. It's going to be half the height of the original. Does that make sense? All right, so I'm going to do the same thing. This is sine again for the parent function. So it's 0, 1, 0, -1, 0. So that's my critical point and trig column. Okay, what I'm taking sine of this time is still just x. There's nothing inside the trig function with it, just x. So there's nothing to the left of this that I have to do. X is done. Those are the x values. Okay, sine of x. Okay, but I do have an a value I have to multiply by. So this becomes 1/2 sine of x. So I'm taking these values and I'm multiplying them by 1/2 because that's my a. So the zeros stay 0 and the ones become 1/2. Okay, so the parent function, I'll put it back up here, was 0, 1, 0, -1, 0. There's the parent function. My new points, 0, 0, so that didn't move. Pi halves 1/2, so it only goes up to here. Pi 0, 3 pi halves -1/2, and 2 pi 0. So there's my new function. So what is the amplitude of this new one? Yeah, it's 1/2. And that's what we said it should come out to based on the equation, right? Up here. So that checks out. Okay, did the period change from the parent function? How wide the graph is, the cycle? No, it's still 2 pi. So how would you describe what happened here from the thin black one to the thicker green one? What type of transformation is this? A vertical compression. Good. So if your a value is greater than 1, it vertically stretches. If it's less than 1, it vertically compresses. These are the exact same transformation rules you've done in algebra and algebra 2, and we reviewed back in unit 1 at the beginning of this year. Okay, vertical stretches and compressions are things multiplied outside the function. That's the same as with quadratics. It's the same as with absolute value, logs, exponentials, rationals. All of the functions we've ever dealt with, that's the same rule, right? Okay. One last thing that your a value can do to your graph. What is my a value here? -1. So my amplitude is what? Say it again. Not negative. Amplitude is 1 because the amplitude's the absolute value of A. So it's still 1, same as the parent function. So the amplitude doesn't change. And what I'm taking sine of is already x. So there's not going to be any change to my period. So far, it looks like there's no change from the parent function because there's not, the amplitude's still going to be 1. But when I look at it and I know in my columns, I have to multiply by A if I have an A. So I'm going to have to multiply by a negative. So what's going to happen to these values when you multiply by a negative? Yeah, what was positive is going to become negative, and what was negative is going to become positive. The zeros remain zeros. So even though the period is not going to change, the amplitude is not going to change, the graph is going to change. Because here's the parent function. And here's the new function if I plot those points with the negatives and positives flipped. How would you describe that transformation? The reflection over the x-axis, right? That's the same transformation rule we've always used. When you have a negative A value, it flips your graph. It didn't change the size of my graph. The amplitude is still 1. It didn't change the width of my graph. That's still 2 pi. It just reflected it. So 3 ways your A will affect your graph. It can vertically compress, vertically stretch, or it will reflect if it's negative. Everybody good with A? All right. All right, so we've already kind of been talking about this as we did the other examples, but the length, or I guess maybe I should say the width, how many degrees or radians it takes to complete one cycle, what is that called? What have we been calling that? Yeah, so we've already been using that term. That's not a new term. That's the period of the graph. That's how wide it is. This graphic that they give you talking about the period, it says that your period is just the distance between any point to the next point where it starts repeating, before the graph starts repeating itself. Okay, so the place that they drew that, I think, is kind of silly. Nobody's going to measure the period there, but you could. That technically is the period. But what you're going to use to measure the period is usually going to be maximum to maximum, so high point to high point, or low point to low point, or a midline point, not to the very next midline point, but to the next midline point where it's going in the same direction. See how it was going down here? It's going down here. So that distance there. Okay, so we're going to use maximums or minimums or midline points to measure our period, but it doesn't matter which ones you use. The period's going to be the same no matter where you measure it. Does that make sense? It doesn't matter if I measure from high to high or low to low. That's the same width, right? Y'all understand that? Okay. So now what affects the period? What's going to change this period from the parent function comes from the b value, the coefficient inside the trig function. So whatever is being multiplied by your x or your theta. Okay, and you use, it's not just b. B is not the period. We use b to find the period. The period is 2 pi divided by the absolute value of b. You're not going to be working with any negative b values, so you really don't have to worry about the absolute value. So if you want to write it just as the period is 2 pi divided by b, that's good enough, because you're not going to have to take the absolute value because I'm not going to give you a negative b. Okay. Why do you think it's 2 pi? Where do you think that, say again? That's one revolution around the unit circle, or you can think of it, that's the period of the parent function, right? Before we do any sort of transformation, you start with a period of 2 pi. So you're starting with that parent function's period and dividing by whatever b is. Now, that's if you know what b is and you want to come up with the period. So like you're trying to draw the graph from the equation. But we're also eventually going to work in reverse, where we're going to be given the graph and we have to write the equation. So given the graph, you're going to be able to just see the period and you'll have to use it to find b to write your equation. So this can be rearranged and solved for b, and it would be 2 pi divided by the period. So the b and the period and the b value can switch. So you need to know that in both directions. All right, so let's try this. So now we're going to use cosine as the parent function. Okay, so I'm going to put my critical points, and to the right of that is always my trig column, and this time my trig is cosine. So what should this column be? What are the cosine values at these critical points? And back to 1. Because cosine starts at a high and ends at a high. It goes high, middle, low, middle, high. Okay, so this is the parent function for cosine. These are the points I'm going to plot. So 0, 1, pi half 0, pi negative 1, 3 pi half 0, 2 pi 1. So here's one cycle of cosine. Now, there's not a column to the right because there's no amplitude that I need to multiply by. There's no a value here. It's an understood 1. So I don't have to worry about multiplying. I'm going to write that out. A is an understood 1. So the amplitude is just going to be 1. No change. There's no negative. It's not going to reflect. So no change based on A. But there is a B. And what does that B do to my graph? What do I use B to find? The period. And the period is 2 pi divided by B. So this will be 2 pi divided by 2, which is what? Pi. So the period of this graph should come out to be pi based on the equation. So once I finish graphing this, I'll measure and I'll be able to check and see if I did it correctly. Okay, so it should end up with an amplitude of 1 and a period of pi. So in our table, I've told you the critical point column is always just titled with what you're taking sine or cosine of. Now this time it's not just x. We're taking cosine of 2x. So a 2x goes here. Now cosine of 2x, that's the entire equation, isn't it? So my y column's done. The y values do not change. But I have a column to the left because I have to get x alone before I have my x values. So what would I have to do to get x alone? How do I get rid of that 2? Yeah, so anytime you have a b value, you have to go backward from the critical point column and divide out the b. So in this case, divide by 2. Quick refresher, because some people struggle with dividing fractions, because I've got pi halves here. If I have a fraction and I divide by something, I have a fraction within a fraction. What do I do? How do I divide fractions? Yes. So to divide fractions, flip the denominator. So 2 becomes 1/2 and multiply. So then that's just pi over 2 times 2. Now, some of you will not need to do that. You understand fractions better than others, and that's great. If you just think about 0 divided by anything, still 0. 0 is not changing. Okay, but this is pi halves, and we're cutting it in half. We're dividing it by 2. Half of a half is a fourth. That's where pi fourths came from. Okay, pi divided by 2 is just pi halves, pi over 2. 3 pi over 2 divided by 2 would become what? 3 pi fourths, good. Okay, and 2 pi divided by 2 would become just pi. Just the 2 over 2 will reduce. So now the x is alone. That's my new x column, my new x values. So when I go to graph this, I'm at 0, 1, so that point did not change. And then I'm at pi fourths, 0. So I go halfway to pi halves, and I'm at 0. And then I go to pi halves, and I'm at -1. And then 3 pi fourths, I'm back at 0. And then at pi, I'm up at 1. So that's the new graph. That's cosine of 2x. Now, I want to label things still. So what is this period of the green one? Is that what we said it should be based on the equation? Yep, we said it should be pi. Okay, what is the amplitude of this graph I just drew? 1. Is that what we said it should be based on the equation? Yes, it is. So you see how it kind of ends up checking itself? If you understand how to read the equation, you can check that your graph meets those requirements. Okay, what would you describe this transformation as? A horizontal compression. Good. Okay, it's like you put your hands on the outside of the graph and squeezed it in. So when your B value is greater than 1, you are going to horizontally compress your graph. What do you think is going to happen in this next one when the B value is less than 1? It's 1/3. It's going to horizontally stretch it. Very good. And we'll pick up there tomorrow.